Okay.
So let's do integration. So that integration is the reverse of differentiation. So I have questions to use, but let's start with the basics. The basic is that this is integral calculus. Integration. So it's the opposite of differentiation. Say that, for example, if I have ax and I'm going to integrate this, to integrate ax with respect to x. Notice that if it's differentiation, we normally set it like this, maybe dy over the x. But when it's integration, the x here is always this way. So you need to know that. So the simple rule of differentiation, the simple rule will say, instead of what we call more like the power rule, is to simply say there is an invisible power here, which is 1. Anything raised to power 1 is 30. So let's say we use this rule, this now, to simply say that the rule of the integration, this thing is to simply say add 1 to that power. So this will now become ax 1 plus 1. Divided by the new power, which is 2. So assuming I have integrate bx squared dx, the simple rule is to simply say add 1 to this power. So this will now become to integrate it to now become bx 2 plus 1. 2 plus 1 is 3, so divided by 3. This is integration. And under integration, we have integration by a U-Substitution, which is the one we'll be doing today. We have integration by U-Substitution. We have integration by parts. Integration by parts. And then we have integration by partial fraction. So but the basic concept, the basic idea of integration is this. And we need to know that there is something we call indefinite integral and definite integral. Just like as I've integrated this, if you finish it, you come and put plus c to show that it's an indefinite integral. Indefinite integration, then plus c. A definite integral is the one whereby, as I'm giving this thing like this, you come and put maybe 0 and 2. We will still get there. Or maybe 0. Maybe from here to maybe 3. They are telling me that there is a boundary. I should go from maybe 0. Or even if I come and I see something like 2 and 3, it's telling me move from initial to final. But any integration where I did not see any of those things, which is what here we are. We've not gotten, I'm just illustrating. We've not gotten there. This is where we are. So any integration where you did not come and see something like values up and down on it is known as indefinite integration. That is what we are doing today. Indefinite integrals. Indefinite integrals. And we need to know that whatever we are integrating is called an integrand. Am I too fast? No. Okay, so see, first is the rule is that we add the power. You know that in the other one, we normally say first of all use the power. That is in differentiation. We normally say use the power and multiply. Then subtract. But here we now say add first, then divide. So in integration, add first, then divide. While in differentiation, you multiply first, then you subtract.
And this English
constant, yes, it means constant. As we saw the examples now, you see the reason for that. So why we normally put this in is that when you remember this is the opposite of differentiation. Assuming in differentiation, I do ax squared plus c or plus maybe 3. You notice that by the time you are doing the differentiation of this thing, you say that there is no x. If you are differentiating this with respect to x, you say that there is no x here. So you just say this is 0 to disappear. Then you differentiate this one. So that c you have here is to say that when you differentiated, possibly there was a number here that you threw away that you said is a constant. So that's what you make room for by putting this plus c, since integration is the opposite of differentiation. So that's the first principle. This principle is important. So with this, we can now start taking examples. So because the mathematics of calculus is not just something you explain. If you like, write 100 notes on it. The main thing is solve, knowing how to solve. When a question is given to you, what is the rule behind? If I see this type of question, what is the rule behind it? So let's take the first example. The first example we have differentiate, let's say 3x plus 2x plus 5. Integrate this differentiate. Integrate this with respect to x. Integrate with respect to x. Okay. So for us to integrate this with respect to x simply means that since everything we have here, the only one that doesn't have x is this. Yes, the one that has 5. Yes. That's the only one that doesn't have. So if we're integrating this, now what we simply do is to make, we say, using the rule of integration, bring this one first. This will now become 3x raised to power 1 plus 1 all over 2. Then plus 2. The x there is having power of 1. So 1 plus 1 all over the power, which is 2. Plus this 5 that is here. This will be 5. Notice that it doesn't have any variable. It doesn't have any variable. But in integration, we will say, since we are integrating this thing now that you have as 5, is the same as saying integrate 5 with respect to x. And anytime you're doing integration with respect to, what it simply means is that if I have just a number and I'm integrating just a number, since it's with respect to x, the x that is here, this will become just 5x. You see it? All like in differentiation we could have said throw this thing away. But once I have just a number, we will say that this is being integrated with respect to x. So for that reason, I am taking it that there will be unknown x here, which is this x. So it will match. So if I am integrating 2 with respect to t, this will be the same as saying 2t. So anytime you are integrating a number with respect to a variable, you multiply. So this will now become 5x. So now I'll come and put plus c. So if you write this way, now this now becomes no, it will leave. See, because the dx is you integrating everything here with respect to the x. This thing that you have like this, is the same as saying integrate 3x with respect to x, integrate 2x with respect to x, integrate 5 with respect to x. So it's the same thing as this. So that's why, as it is set up like this, what the x here is telling you is that everything that is inside here, that you should integrate it with respect to the x. As when I come here and see with respect to t, I can't integrate this. Because this thing is what everything here is carrying is x, not t. So the only one I'm integrating in that case is just this one that's not carrying a variable. So for that reason, if I write this way, it will be 3x squared over 2. plus 2x square over 2x square. 2 will cancel 2. Notice that 2 will take care of 2. 2 and 2 will cancel. So this will become x squared plus 5x plus c. That's the final answer. So what we are doing today is introduction to integration. Then we will do integration by U-substitution. Then we'll be done for today. So let's try something a bit more serious. I like it. It's the same thing with this one.
Okay.
But just what I'm saying is that if you have the number written together like that, if you integrate this thing now, just this will be the same thing as saying 10. X will be 1 plus 1 over the power line is 2. If you integrate this one now, it will be 2x 1 plus 1 all over that power, which is 2. If you integrate this now, it will be 5x. That is, if you integrate it separately, that is what it will be for each one. But the other one added plus to it. So that's why I brought it out to show you what it is. So if you integrate this one individually, it will have just this. And when you finish, each one now will come and carry plus c, plus c, plus c. C means constant of integration. What you integrate is known as an integrand. So let's say I have 3x squared all over x cubed minus 4 dx. Now let's integrate this. So once we see integral sign, this thing means sign of integration. Once we see this thing and there is no number on it, maybe down and up, it means indefinite integration. Indefinite. So the first thing you need to check is now between these two things. You see that the one that has the highest power, that is between the two variables, because we are integrating with respect to x. Between the two variables, you see that the one that has the highest power is this one. Because it has 3. The variable here has 3. This one has 2. So we just say, let u be equals to x raised to the power 3 minus 4. So anytime you notice that there are variables given to you, like what you are given is having variables maybe in a way that is a function of a function, like this is a function of this one. I can integrate only this thing. I can integrate only this thing. So we say it's a function of a function. So if that be the case, in that case, and there is division to it, it's not addition. Once you don't see addition or negative sign, and what is separating the functions are division or multiplication, you apply U-substitution or by heart. What we are at is integration by U-substitution for now. So I'll say let u be equals to this thing that is at the denominator. So if u becomes what is at the denominator, I will in that case say that means that if I happen to differentiate, because see this is the x that is here, this thing means changing, and changing means differentiation. Let's integrate everything here with respect to this. So I will say du over the x of this thing now will be simply, if I differentiate this u with respect to x, it will simply be like this 3 here. Come over to the 3x, 3 minus 1 will be, this will now become equals to 3x squared. And you know that if you differentiate from 0, it will just leave. So this becomes the u over the x is equals to this. If I want to make the x subject of the formula so that I can replace these are rules. Once I see that it's a function of a function, there is a variable and there is another variable having different powers. And what is separating it is multiplication or division. I quickly want to change this dx. I will quickly try to transform this dx so that this dx will leave. I will replace it with what I have here. So if I make the next subject of formula here, you see that this will become du equals to 3x squared dx. Now trying to make the x subject of formula will simply mean that and this pattern we are using works when the one power is greater than the other one. This has bigger power. The one with bigger power is when you make u as subjects as your u. So this will now be the x will simply be equals to from here to simply be du over 3x squared. So I've been able to get the x. So I will carry this thing I have for the x, come back and substitute it here in this equation, so that I will now have integral 3x squared all over x cubed minus 4. Then the x that is here, I will replace it with this to be du over 3x squared. The goal of every integration is for you to replace everything that has x or any variable to u when you're using U-substitution. For you to change everything that has x to u or everything that has a variable that is not u to u. So notice that when we started, we select this and this. Everything here be u. So I can say that this is the same thing as saying integral 3x squared all over u. Replace this with u. So all over u. Now notice that if that is true, I now have the u over 3x squared. And notice what is separating them now is multiplication. So notice that this can cancel this. So this can take care of this. So that I now have integrate 1 over u with respect to u. And 1 over u. Once you see anything like 1 over u or 1 over x, 1 over anything when it has to do with integration is the same thing as saying len. This thing is the same thing as saying len u. This thing is the same thing as saying len u. If you integrate this, if I ask for example, see what I mean? Integral of 1 over a or 1 over b or 1 over c or 1 over u, anything, integral of it is simply len, natural number. Len means natural number. Len u, then plus c. So once you know this is not the sentence. Go back and remember that u means something. U means this. So this will now be len s cubed minus 4 plus c. So somebody somewhere might choose to say this thing could have been the sentence as saying integral u raised to the power minus 1 du. If you do it like this, it's still valid, but this is the better option. Once you see anything over a variable, once you see 1 over a variable, 2 over a variable, that thing is simply the sentence as 2 len u like this. So see what I mean? If I have 2 over u, 2 over u is the sentence as saying 2 times 1 over u. So this is the sentence as saying 2 len u. Natural number. It means natural number. Natural number. So that's for the first example. Let's take the second example. Let's take the second example. Are you done with the writing?
Yes, sir.
Okay. So you check if there is any part that is confusing you as we solve the next question. You pay attention more to it. So I will solve another example like this one now, so that you master the pattern. So let's say I have 8. Let's use this one. Let's say I have integrate 4x root 20 minus 2x squared x. So if I have this kind of question, the first thing I need to do is to simply look at these two things. This one is having a variable. This is also having a variable. But what is separating it is not plus or negative sign, but multiplication. Because this thing makes the sentence saying times. So for that reason, I will call the one with highest power my u. So I will say that everything here becomes my u. So I will say let u equals to 20 minus 2x squared. So if I get that, the next option, so first of all, the one with highest variable, this is step 1, the one with highest variable becomes your u. The part with highest variable, because this is 20 minus 2x squared, the part with highest variable becomes your u. I could have said that this with u, but this is having highest power, this x is having highest power. The next thing now after I do this is to find a way to replace this x that is here with the differentiation of this thing. So I can say the u with respect to x will simply be, if I differentiate a number is 0, so this is going to be 2 times 2, this is minus 4x, 2 minus 1 is the same thing as 1, and anything less to 1 is this is it. So if I want to now get the x from this, it will simply say the u equals to minus 4x dx, making the x solid formula, the x will be equals to the u over minus 4x. So I can now carry everything here and replace for this. So that this becomes, if I write this now, it becomes integral 4x root, everything here is u, we replace it with u, root u, then the x, we replace it with minus the u over 4x is the same thing. Minus down is the same thing as minus up. So I'll replace it. Now that you've replaced it, remember that this thing is being separated with multiplication. There is this thing here, that's what I replaced. It's being separated by multiplication. So you can very well see that if that is true, I can as well write this term like this: integral 4x. Square root of u is the same thing as saying u raised to power 1 over 2. In indices, if I have m roots, maybe k root m, this thing is the same thing as saying m raised to power maybe 1 over k. So the denominator becomes the root, while the numerator becomes the power. So anything raised to power 1 is still that thing. So if I have this thing here, this square root raised to power this numerator, which is 1, and anything like that is still that thing. So that means that this u here, root 2 is the same as saying times u raised to power 1 over 2, then times minus the u all over. Okay, let me do it this way. Times minus, or let me use something like this so you don't think it's x. Minus the u. Minus the u. Everything here over 4x. This and this, they are the same thing. So you can see that since this is 4, you can cancel this. X can cancel x. So that I now have integral of u raised to the power half. Now the minus sign I have here, I can bring it out to this side, minus the u. So that by the time I finish integrating, I can bring the minus back. So I can bring it to one side. So this is now integral u raised to the power 1/2 with respect to u. So if I integrate this, integrating something means add 1 to the power, divide by the new power. So if I'm integrating this now, I'll bring the minus down. Then I say u raised to the power half plus 1 all over. Now 1/2 plus 1 is the same as this is 2 here, 1 plus 2. This is 3/2. So 3/2. Now, yes, that is add 1 to this, divide by the new power. So this is the sentence as saying minus u 3/2 all over 3/2. And notice something. This can also be the sentence as saying minus u 3/2. Okay, if you have divided by 3/2, reversing it, if you introduce multiplication, reciprocal law, this will be times 2/3. This one, remember we said in integration, we normally do add 1 to the power, divide by the new power. So if I add 1 to 1/2, you get 3/2. If you add 1 to 1 half, you get 3/2. Do it. If you do it, you see.
1 plus half.
Yeah, no, this is 1/2. Yes, 1/2.
So you don't call it half.
Yeah, even if you call it half, half is 1/2. Half is the sentence as 1/2.
Yes.
So if you
1/2 is half.
So
1 plus half.
no, see what? Yes, if you do, see what it means. 1/2 plus 1. So if you add 1 to 1 plus 1/2, is the sentence as saying anything 1/1 is the sentence as this one. Take the LCM. The LCM here is 2. 2 divided by 2 is 1. 1 times this one, 1. 2 divided by 1, 2 times 1, 2 plus 2 equals to 3/2. So even if you punch it in your calculator, half plus 1 is 3/2. So that is how you get this. That is how you got this thing. That is why I said if add 1 to the new power, add 1 to the power, divide by that new power. So that is what we do. This 1/2 plus 1 is the same thing as this thing. Divide by that. So when I say that if you reverse this, since we've integrated, if you reverse it, when you have u raised to the power 3/2 divided by 3/2, this division. If you change it to multiplication, 2 will come up, 3 will go down. So this is the sentence I say if you put times instead of division, because notice that there is division here. So this will become 2/3. That is what I do. So this is how it is the sentence I say minus 2u 3/2 all over 3. So you can now say that this is the sentence I say minus 2, we replace u. When we started, our u is 20 minus 2x squared. So raised to the power 3/2 all over 3. So this is our final answer. Our final answer is simply minus 2/3. 20 all into 20 minus 2x squared all raised to the power 3/2. So if I want to maybe simplify further, I can say that this is as a minus 2/3 root 20 minus 2x squared raised to the power 3. And see this is still the same thing. next example. The next one is when the powers are the same. The powers of the two variables are the same. So let's find a question you can use for that. Okay, yes, I've seen it. Let's use Are you done writing?
Yes, yes, sir.
So check if there's any part that is confusing. Just call me so I clear your notes.
So you're saying that integration is the opposite of
Differentiation.
this integral calculus.
Yeah. That's it. Integral calculus is integration.
Okay.
Yes. Integral calculus is what is integration. Why differentiation is differential calculus.
The calculus is a visual.
Calculus is more like, or should I say, a branch of mathematics, a branch of engineering maths that is concerned with domain and range, like domain and range, integration, differentiation. So it's more of, or should I say, it's more of advanced level maths. In pure maths, you deal with algebra and trigonometry. While in calculus, you deal with integration, domain and range, and differentiation. So all those maths that involves, should I say, a second level maths, that's calculus. So I don't want to use it for what it is because the word from calculation you get calculus. So but just know that once you hear calculus, anything that talks about calculus is a type of maths that revolves around integration, differentiation, domain and range. Just because if you tell somebody mathematics, that is pure mathematics, the person is thinking of algebra, trigonometry, geometry. Once you tell somebody calculus, the person is thinking of integration and differentiation. So with that said, let's take an example. So calculus is like it's just like if you come to first semester maths and say pure mathematics. It's just what calculus is. So but the topics under it is now this differentiation and integration. So we have an example. This is we have integrate 2x root 4x. That's why some people will tell you that calculus is like further mathematics, but all of them are mathematics. It is. You said?
Is it not further?
But you know that if in normal, further mathematics is just word they use in secondary school, like to differentiate pure maths from calculus. You understand? So in secondary school, you only hear teachers tell you calculus is calculus, they call it further mathematics. But in normal, let's say you come to mathematics as a course now, nobody will come as a course in mathematics and tell you there's something like further mathematics. There's nothing like further mathematics in mathematics as a course. So it's in secondary school they use that word further mathematics. So normally calculus is simply maths that involves all those engineering maths and maths that touches all the other levels of science. That's calculus. Because in calculus you have even physics, like all these dynamics, courses that concern physics, even chemistry, all the type of mathematics that involve different courses. You call it calculus. But in secondary school they just say it's further maths to tell you there's touching other mathematics. But somebody in the maths know that there's nothing like further maths. It's just calculus they're talking about. So to integrate this, now notice something. You see that the power I have on this is the same power with what I have here. So once you notice that the power you have on the variables are the same, once the power you have on the variables are the same, and they are being separated by multiplication sign, All you just need to do now is to check, make your U the one that is looking complex. So your U will always be found using the one that is looking more complex. So I can say let U equals to 4x minus 5 in this case. The minute I make this 4x minus 5, I need to now go back and find a way to get x from this. Let's get x here. If I want to get x here, you see that this will be the same thing as saying u, this crossover plus 5 equals to 4x. If I want to get x here now, I'll say divide both sides by 4, or say divide by 4, so that x will simply be u plus 5 all over 4. So let me put it to one side. I've gotten x to be u plus 5 all over 4. So the next thing, so what it means is that by the time I come, I will replace anywhere I see x with this. Because our goal in differentiation, once we're using U-substitution, is to replace everything that is a variable that is not u with u. So I will first of all get, because why I'm using this method is because I've noticed, so it's always important to notice, once you look at the question, you look at how it appears. I look at this and I see that the variables I have here, their powers are the same. This is not like 2 and this one is just having 1. They are having the same power, 1. Once it's so, you must find x before you now progress of finding the x. So in order to find the x, I will use the same pattern I normally use. The u over the x from this first place will be equals to 4. Because by the time you do, this can't have, you can't differentiate this will be 0. And if you differentiate this, it will be 1 minus 1 times 1, because the power of this variable. So you see that this will be x raised to the power 0 times 4. And anything raised to the power 0 is 1. So it will be just 4. So that is why I say that it will be 4. So if I get it, the u will be equals to 4 dx. And that means that the x will be equals to the u over 4. So I've gotten x and I've gotten the x. I said, whenever you're integrating, if the powers are the same, the powers of the variables separated by multiplication or division are the same, you will first find x before looking for the dx and substitute. And remember, why you are doing this, because the separation is with multiplication or division. As we maybe I see 2x plus 4x minus 5. I don't need to do that. I'll use that first method when we started. We are just integrate and 1 to the power, and 1 to this one. Divide that. So now that I'm done with this, I can now go back and substitute everything I now have. So this becomes, if I rewrite this now, it now becomes integrate 2. Remember we said find x. So anywhere I see x now, this will now be u plus 5 all over 4. I've replaced x. Now, roots. This root, what is here? We said let this thing be u. Then the x, we got the x to be the u over 4. The u over 4. So if that is the case, this will not be the same thing as saying integral. Okay, let me just take the 2 outside. 2 is a constant. These 2 can go outside. So I now have u plus 5 over 4. This root u is the same thing as saying u raised to the power 1 over 2. Then the u over 4. The u over 4. So since I have everything here is certain like this, I can put everything here like this. So when I have something, do you know that a squared times a cubed is the same as a raised to the power 5? But a squared plus a cubed cannot add. However, what you can add is maybe you do a squared into 1 plus a Because if this times this, you get this. If this times this, you get this. But they cannot give you this. So if I know that when I see this 4 that is here, and notice that what is separating this is plus, I will just leave it alone. But these ones that are separate, I can just say 4 times 1 is 4. Now, notice that this one here is anything on this one is over 1. So I can just transfer the 4 here to this place so that I have 2 over 4 integral u plus 5 over 4. Then times u half. Then the u. And write this way. So one thing about integration is that once you learn it, the next thing is carefulness. You use the carefulness to study the pattern to dictate what the question is all about, to dictate what type of method to use and solve it. This calculus was invented by Isaac Newton, and it's not a math that you solve just going straight forward. Everything you are solving has its own rule that is guiding it. So once you obey that rule, you'll be able to solve it properly. Let's say, for example, I started this thing without knowing that I will change this dx. I will get an answer, but the answer I will get will not be the correct answer I'm getting now because I did not follow the rule. So when it has to do with integration, all these things, all these rules and factoring out must be obeyed. You must notice when the variables have the same power. Notice when they are separated with multiplication or division, what you do. So once you know that, there will be no issue. So then I can here, I can easily say multiplication. If I have a plus b, then times c. This is the same thing as saying distributing power law, ac plus bc. This can go here, this can go here. So if that be the case, it can happen here. This can be 2 over 4 integral, if this come here, to become u times u raised to power 1 over 2 plus 5 u raised to power 1 over 2. Now, all over 4 the u. Now, notice something. In indices, we normally say that if I have a times a, that is the same thing as saying a raised to power 1 plus 1, because there's 1 here, there's 1 here. If I have a square times a square, it's the same thing as saying a raised to power 2 plus 2. If the bases are the same, add the powers. Why the division law is if the bases are the same, subtract the powers. So if that is the case, since these two bases are the same, there's an invisible one here, anything on this one. Since these two bases are the same, this will be the same thing as saying 1 plus 1 over 2. And anything on this one is over 1. So if you do the same thing 2 here, 2 will divide this 1 times this, it becomes 2 plus 2 divide itself 2 over 1 times 1. So it becomes 3 over 2. So now that I've loaded it, I can now go back and say this is the same as saying 2 over 4 integral u raised to power 3 over 2 plus 5 u 1 over 2 all over 4 the u here. Yes. Now at this point, I can now, I want to clean this. I can now, because I need freedom. That's just what I'm trying to illustrate. At this point where this thing is like this, I can now say, since they are being separated with plus, I can say, let's, because this thing that is here can still come and multiply this. So I can say, let this now go here. Or instead of us getting confusion, let's carry it along. So that there will be no confusion. I will say 2 over 4. Integral, you know that this thing is the same as saying u raised to power 3 over 2 over 4 plus 5u raised to power 1 over 2 over 4 the u. Should we know that it's the same thing? Because if you get the LCM here, it's still 4. So they are the same thing. So but why I did it like that is so that I can integrate. So that if I have to integrate that now, I could have said carry everything here and times here. But because of the fact that not everybody understands this differentiation, that's why I'm taking it one step at a time. So this will now be the same as 2 over 4. Integrating this one will mean that this will become the same as saying 1 over 4 that is here. Okay, let me write this first. This thing that is here is the same as saying integral 1 over 4 u raised to power 3 over 2 plus 5 over 4 u raised to power 1 over 2. So if I know this, integrating this now becomes the same as saying 2 over 4 into 1 over 4 times, this is going to be u. To integrate this is this one you're integrating, not the numbers, the variable. So this will be the same as saying 3 over 2 plus 1 all over. So if I do 3 over 2 plus 1, this will be the same as saying 2 here, 1 times this 3. 2 here, 2 times this. So 5 over 2. So 5 over 2 plus plus 5 over 4 u add 1 to this, you have 1 over 2 plus 1, which will be 3 over 2. So by the time you do this, you see that you are now getting, I could have done this, carrying these things out, but I don't want issues. That's why I'm taking each one at a time. So this is going to be the same as saying 2 over 4 root 1 over 4, then u 5 over 2. If this is dividing, that means this can be the same as saying times 2 over 5, then plus u, this is 3 over 2, remember there's 5 over 4 here, then times 2 over 3. So if that be the case, if I now try to simplify further, this will now give me, let me clean this side. This will now give me, this will now give me 5 times 4 is 20. 5 times 4 is 20. So it will now give me u raised to power 5 over, okay, 5 over 2, yes, 5 over 2. Notice something, I'm trying to do everything for this side u. So it will be 2 times 1, 2. Then, remember this one is power. So it will be 2u raised to power 5 over 2 all over 20. Then, plus 2 times 5, 10. So plus 10 u raised to power 3 over 2. 10 u raised to power 3 over 2 all over 12. Yes, now I'm coming. Not everything is multiplied by 2 over 4. You say, how did you get this is 5 over 4, children. U raised to power 3 over 2 times 2 over 3. 2 times 5, 10. 3 times 4, 12. That is it. So that is how we got it. So if you check now, you see that this can become 1, this will become 10. If 2 go here, you get 5. If 2 go here, you get 6. So this will be the same as saying u raised to power 5 over 2 all over 10 plus 5u raised to the power 3 over 2 all over 6. Still everything multiplied by 2 over 4. And this is now when we can now say this multiply this multiply this. So how we do it without trying to multiply error is so that we don't have any confusion. So that this now becomes 2u5 over 2 times 10. 4 times 10 is 40 plus 2 times 5, 10u3 over 2. Then 4 times 6 is 24. So by the time you do it, something can still work here. 2 here 1, 2 here 20, 2 here 5, 2 here 12. So this can be set as saying u5 over 2 all over 20 plus 5u raised to the power 3 over 2 all over 12. So I can replace this u that is here. When we started, we said let u be something. What did we say let u be when we started? Check what we did here. Guys, for this example, 4x minus 5. Yes. So I'll replace u with 4x minus 5. This will be the final answer. So if you finish writing, check if there is any confusion, so that if possible, we'll use another example to do it gradually.